Hello, Dr. Mike here with CIS-2640, which is network security, or I always call it Security Plus class. Over topic 4, Advanced Cryptography. So hopefully you reviewed the basic cryptography lecture. This is, at the time of this recording, this is our textbook, chapter 4. Again, the title may be a little misleading. It says advanced. We're not going to be running the mathematics algorithms here, of course. We're looking at really is application of cryptography. So, as before, I'm cherry pick some slides here, bring up some things, and show you some actually one of the tools I've used in security auditing that really comes into play with this chapter. So, with that, let us begin. So, again, implementation of cryptography, it's very important we understand not only how it works, but how it's implemented and what parts of these are implemented in certain ways. Specifically, key strength, the mode, our input values, initialization vectors, how things are sort of set up. So we know it's a block cipher mode, let's say, that's fine. We know we're using a NIST-approved cryptography library in our coding, maybe for our database encryption. But how's a secret key created? What's that key strength? So there's areas of how it's set up is very important to understand. So first off, of course, is randomness, key length. How's the randomness created? So on that, we talked about RSA in the previous topic, the public-private key. And a lot of times sites for shopping and things like that will generate unique one-time use RSA key pairs for the session with the client. And of course, generation of that much needs a large amount of randomness. So how do you get that randomness? And again, I think week 3 I talked about it before and how important it is. There's actually a really great video here. I don't know to do the whole video. But you'd be surprised where randomness comes into play.
Computers aren't very good at picking random numbers. Every part of a computer is designed to be predictable and follow logical patterns. You put the same numbers in, you're going to get the same numbers out, which is a problem because all modern encryption, including that padlock up in your browser that tells you that you're safe, all of that relies on big, properly random numbers.
So again, I'll pause it here. I'm getting some weird syncing while recording here, so with the voice is off. But again, I'm not going to use this whole video. I actually have it part of my playlist. It's a really good video. You could probably guess by behind the back of there.
I'm here at the headquarters of Cloudflare in San Francisco.
Cloudflare is a service that protects websites and web services and sort of sits in front of them as a gatekeeper. Somewhere around 10% of the web flows through Cloudflare's network.
So again, sorry to pause it. I'm not going to use the whole video. Previous videos I've done in other classes, I'm getting some YouTube copyright stuff against me. I'm just going to summarize it. This video is part of the playlist for this class. So watch it if you watch the whole video. But look at that. It's a wall of randomness. And not just inside the lava lamp itself, where the bubbles are at, their shape, their dimensions. The lighting too talks about this. The lighting that you see that's used to generate the random nonces. So if the lighting's off a little bit, down to the pixel, things will change. So trying to guess the randomness, guess where every single one of those bubbles are going to be with certain lighting conditions for that many lamps is basically impossible, at least impossible with the amount of time you would need to hack something. So the idea is it's hard to find the randomness behind something. That's important to understand that too. So key length, again, the longer the better. I mean, if your key length is a 4-digit code that's entered by the user, which becomes that becomes the initialization vector, that 4 digits, and that's going to be the length of it. That's pretty bad. Whereas if we pull, 256 swipe of a good random nonce, use that for our key length, generate our key, that's going to be a lot stronger. Also, crypto period, how long is this key used for? Is it a full-time key, something that's always used? Is it just for session-based keys? And you'll see a lot session-based use is probably a lot stuff for web-based traffic. So cipher block modes, I'm going to skip over that. So thing is how we provide our keys. What takes care of key generation, storage? How does it all happen? This can be done, what sort of implements the algorithms themselves. This can be done either hardware, software, or both. For large providers, you actually might have rack-mounted security or security service type devices. Some servers come already built in with a security platform that can actually do a lot of random generation and also store separately private keys, perform separate authentication, things like that. So these crypto modules. This figure out of the textbook was pretty good. I kept it. It just shows you in Windows itself there's a service called cryptographic services. So it could be just a service that runs in the background up to a rack-mounted device. So again, understanding what that device is or what that service is very important. Maybe when doing a security audit and verifying the cryptography implementation. So a couple of things too. Again, we talked about nonce already. Number used once. It's used once. It's not cherry picked from over and over again. Assault. This is really important. This is really important when it comes to passwords. So even if I have a strong password, it can be put into rainbow tables, hence a known hash of that password combination. And these are pre-generated already and called rainbow tables because to generate all, a couple million different types of combinations of passwords takes a lot of computing power. So you download these big rainbow tables, that hash is already there. So you can basically just start comparing hashes. And of course, most of the time it's the most often used passwords at the top of the stack, right? Password 1, 1, 2, 3, 4, and so on. You always shoot for the low-hanging fruit, right? And so the idea is if I have a dictionary-based password, maybe it's dictionary but it has a couple of symbols at the end of it or has a number, still can sort of be guessed. Maybe sometimes with a plain text attack, or using a rainbow table. So add an assault is a random value from a nonce, and that's stored separately, but combined with and held, used for the authentication. So if someone wants to download or let's say breach a website, get my password hash, it has been salted. So not knowing what that salt value was, I can't reverse the hash to figure out the password. Hence, the nature of hashes that cannot be reversed engineered or so reversed. So I can't go back and get a list of hashes from a place I may have had a data breach with, and sort of use those, not knowing what the salt values were. I can add those with the salt values, but now with the salt values, it's become so unique, it's not really useful anymore. So if it was password $123 that was hashed with the salt mixed inside there, it's going to be harder to go and use that. That's proper way to password storage should be done. Anyways, so let's leave it there. So that's understanding how cryptography is applied. That's our first step. Understand sort of the nuances, not just how it works, but how it's implemented, and those ideas of noncing, random generation, key length, and also key management. Now the next level we have here in play, which also comes into play when we have public key encryption, is certificates. Now certificates you might know of right away from websites, like you see here on my screen. And we're going to come to this in a second, but these are also used in when I transmit my public key. A lot of times you also will transmit a certificate for that public key. The idea is you're not getting a key for someone who's an imposter of me. Hence that way you're not sending someone you think is Dr. Mike, maybe some confidential information, and it's not. So we have the certificate in place for our public key infrastructure, or PKI. So these certificates have certain things about them. I'm not going to speak the slides to you, but go in and find in the chapter where it talks about the uniqueness of the signature. So you should be able to validate a certificate. and how the trust is done. So how do you validate a certificate? Well, there's a rings of trust we use for this. We trust that, in this case, this is a side example here. This is Komodo. We trust Komodo EC domain validation service says this is bookshelf vitalsource.com or vitalsource.com probably. And so Komodo is sort of a third party, a trusted third party that can validate the certificate. Again, we see it here in the browser. This is also done for PKI. And these are called certificate authorities. A lot of tools behind this, and this is one of those transparent things we don't see. We see the lock in the web browser. We trust it's good, but there's a lot of stuff here. How it's signed, of course, digital signing. Is it a public-private key? Is it just is it a certificate of authority saying something, a CA who they say they are, and in our case, Vital Source website, who authenticated it. So again, how we store, these things are stored, and how they're handled. They can be the revocation process, revocation lists. There's a protocol we have, OSCP, to help with this. We have OSCP stapling. We get regular intervals, sort of get a updates on our certificate statuses. There's root certificates. We have certificates for hardware. Software has certificates. Domains have certificates, which that one we know of. And with certificate chaining, so there's a lot of stuff with certificates here. Again, I don't want to read the slides to you, but be aware here we have this certificate chaining here. So Equifax as a digital provider, and they say they trust GeoTrust. GeoTrust is intermediary, and then buy_online uses a GeoTrust certificate. So, who trusts Komodo? So, right? So you going back to this certificate here on this website I'm looking at, So who trusts Komodo? Well, here's the serial number, here's a version, here's our algorithm is used, and SHA-256. There's end validation times, so these have an expiry date. Here's a public key. They left a curve for it, so here's the algorithms that were used. They use a public key algorithm. Here's a version of it. So this stuff can be checked. Now, there's a lot of stuff here. You think, wow, this is more than just verifying that Komodo is who they say they are. That's done through this trust here, right? Somewhere, maybe it could be Google. There's root certifiers who certify third parties. And I'm going to go off the slides for a second. Is it an extension and so on? So this is a lot of stuff here. Here's the actual SHA. Here's the fingerprints for it. So we understand the uniqueness of this. So we can make sure this is actually a real certificate. So how do you check this? Like how do I verify this is all good? Well, there's some great stuff here. There are a lot of tools. I'll show you one I've used in security audits and also in pen testing. It's Qualys SSL Labs. And you can plug in the domain name here. Like I put sinclair.edu, hit submit. I won't do it here. It takes a couple minutes for it to run, but you get a report card back. And we talked about some things with encryption-based attacks. One, of course, is can we do a downgrade attack? So in this case, this server accepts RC4 ciphers. So those are older protocols. It does not support authenticating encryption, cipher suites. It does not do forward secrecy when referenced in browsers and so on. So it gets graded. And you can see the information here about the certificate. Now again, this was from I pulled two examples from these recent lists here, recent best, recent worst. You can run this against any website and it will show you. You can see TLS 1.0 is encrypted, is trusted. That's bad, right? I can force a lower level encryption protocol. Now I do this in a downgrade attack. Normally, if I run as a standard user, I always ask for the best encryption, which in this case is 1.2. 1.3 is not yet. And this case, they trust TSL RSA with RC4 hash. This is an insecure cipher suite. So you can see you can use this as an attacker to sort of really start planning an attack. Use it as a defender to see where you have your weak points. Handshaking simulations here. So what is handshaking anyway? So I'll show you in a second. Let's look at a bad one. This one's got an F. So first off, it's not trusted. And again, you can see, I won't click on, well, let's click on these links here. More information. This will tell you about why RC4 and TLS is broken, now what, right? And then good part about this is if you are a security analyst, security engineer, and you're tasked to do a security audit, you're going to communicate back up your results to folks that might not be too inclined to understand what it means by just, I know encryption is, but what does RC4 mean? You know, why are we at a B? Again, you don't have to do too much research. This website will take you down that road and give you some information you can use to maybe summarize and say how we need to fix it because of these certain issues, or it might explain why it's there. Some browsers still need it, and so on. So great stuff here. You can definitely get this. And of course, why is it not? This one is on F. First off, it's not trusted at all. So invalid certificates. Now, look, invalid certificates, a lot of times your browser will give you a warning right up front on a browser, but also the PKI should also not allow, it will log and not allow improper certificates. So common to see this, of course, with self-signed certificates. Self-signing meaning I create my own certificate, use it for my own encryption. And you think, why would you do that? A lot of times, if you do any kind of software testing or server testing or in-house testing where you need to want to test that TLS is running, but you don't want to pay the money for a test certificate. So you just do your self-signed certificates. Very common. A lot of times you can set those in your browser. And it's not uncommon to see that in a lot of software testing departments will, you know, as part of their standard protocol, to go ahead and create a self-signed certificate, and then within the test process, just allow it for the server, and then proceed with the software test. So, replication. This is definitely not trusted at all. So again, that's a bad one. Again, SSL Labs, fantastic way to look and do this. So again, slide deck. There's domain validation, extended validation, wildcard certificates. You can probably imagine if I get an extended validation, that's wildcard from all my entire domain. It's going to cost more money, but it is an investment to have that. And this is also why you see subdomains used, like at Sinclair, elearn.sinclair.edu, students.sinclair.edu, because they all fall underneath the sinclair.edu certificate, domain certificate. So how these certificates handled. So here we see in this is actually a really good figure 4-9, the key exchange. How's it happen? So this is a summary of it. I actually have a little more detailed one here. And this picks up here after our initial TCP/IP, our SYN-ACK sequence, right? Our three-way handshake, SYN, SYN-ACK, and ACK. And after that, it kicks off and goes over to this process. Our hello, okay. What kind of do you support encryption? Yes, I do. Let me see your certificate, and so on. And when we get to the second part, we actually do our authentication. We actually do this over Diffie-Hellman. So Diffie-Hellman is sort of the way we communicate, and it's a process used to determine the communication of these certificate parameters. So keep that in mind. You'll see that somewhere in a test probably. And a lot of times, after our TCP session is established, our TLS negotiation is done, it might be done over a temporary certificate or temporary key, usually called a sort of a temporary key negotiation. And after that's all done, when everything's agreed upon, then we'll do an actual session key. So there could be more than one key used, even in the initial connection here. So keep that in mind here. You see this in the certificate exchange. When it's all done and complete, of course, we see the secure in our web browser. We trust our web browser. Up-to-date modern web browser will ensure our security. We're talking with someone who they say they are. In this case, Google.com. extended validations for more information, like Twitter here, things like that. I'm going to skip over this. Again, machine code, email. We can see certificates in other places. A lot of times they can put onto laptops and use to certificate authority with the OS. The idea being if someone pulls a hard drive of a laptop and puts it in something else, that certificate, which is held in the trusted platform module chipset, does not match the operating system. That the other side of that certificate doesn't match, and will basically allow it code signing. We get this through applications. When you download an application from an app store using like on a mobile device, there's a certificate involved in that, and that code is sort of signed as it did come from Apple, or it came from the Android Play Store. And emails, people don't use it too much, but you can actually create your own private certificate. And create a public-private key pair and encrypt your own emails. So this is beyond the regular encryption that would be done with the transmission. This is for the storage of and reading of emails. So just standard here, I'm coming from this. Only thing from this I'm going to come across is it's called the X509 standard. So again, look for the textbook for details upon that. No surprise, all this process, we came from having standards in encryption algorithms. Now we have a standard based for how we exchange keys and digital certificates themselves, how they're configured, and how they're sort of verified. So PKI is the way we do this, public key infrastructure. Again, it's sort of a way we sort of pass off our keys here. This is a nice little end-to-end example here. The thing here is that the important part is we understand this is an RSA, so we have prime numbers and encryption in play. But really, when my public key is put out there, there's a certificate attached to it that verifies that's my public key. So you can do some verification there too. Again, it's for asymmetric cryptography. So again, PKI, we can create, store, revoke, distribute our actual certificates to other PKI management frameworks and other providers. So trust models, I think there's a graphic for this. There's hierarchical trust, which just means there's one authority, and all the certificates I have point to that one authority. More in play, though, we have distributed trust. So there's an authority in play here, maybe Google, and then maybe Komodo. I know who Komodo is. Again, I think I showed this already before. Understand that there's a distributed trust model and something called a bridge trust. The facility doesn't actually issue certificates. Instead, they actually use a hub. That's an important thing here with the bridge. So our hub here will help get certificates out. So there's a huge model here of different hierarchies for how certificates are trusted. So again, policies, practice statements. Probably no surprise that these certificate authorities, it's important for them to be secure. If they ever get hacked and the hacker can create trusted certificates and use those in an attack, that's a very valuable resource as an attacker. So again, there's life cycle here. This is a pretty important slide. This is probably going to be, you'll see this probably on exams, even cert exams. Understand the life cycle. It's creation, suspension, revocation, and expiration. Again, so the idea here is, revocation, suspension. Someone may leave temporarily in this example here. So you would sort of put on, so sort of pausing that certificate usage, and you can always bring it back. You can, bring it back to creation mode or bring it back into active mode. Whereas revocation is no longer valid, expiration is expired. So management, again, storage, usage, and handling, very important. Public keys, make sure that when they are put out, they're put out with the proper channels so they can be validated. But also private keys, you don't want those to get out at all. Private key storage is pretty important. And public-private key, backing them up is important. The backups are secure. Key escrow. A lot of times we actually take a private key and escrow it out or send it out. Even our public keys might be held in different ways. And there's actually an example of this. Skip over the key handling here. Here we have our key handling. Is our public key. We actually can store parts of it, the certificate itself, in different groups. That's the idea. It's not one. There's not one person that holds the key itself. It's called M of N control. And with this way, you can sort of break out parts of the key. So part one does not. All they know is part one. They might know who has part two, but they don't know who has part three, and so on. And they can't see part two. So if one of these is ever hacked, you don't have the entire key itself, the public key. So, and the last part of this chapter here, probably the most important one, of course, is, and it's going to be probably somewhere in the part two here in our chapter summary. And this is probably the first thing you'll come to as both a security audit, a security analyst, and also maybe a pen tester or doing a security assessment, is make sure these are actually being used. The protocols are being used. So I talked about already, everyone knows HTTPS. Well, there's old protocols in place, email, terminal connections, secure socket layers, and so on. So you want to make sure we use SSH and not Telnet. We use HTTPS and HTTP, especially where we have confidential information. No surprise, everything that goes with the network, if it's not using TLS, which is TLS and SSL are the same things. SSL is just sort of the old name for it. It's not using current modern TLS. It's important because TLS does get aged out. With a good key, it can be cracked. So, and of course, if it's not being used, there's no TLS at all. It's called clear text. So, I know in previous labs you've already seen it where you can see the FTP credentials right there in Wireshark. So, secure shell. So this is one of the important ones. Telnet is an old protocol that's still used in a lot of places. If at all possible, it should be replaced with SSH. slog and SSH and SCP are part of the utilities of SSH. I think it was rlogin, RSH, and Telnet were the three unsecure ones. Keep that in mind. Of course, HTTPS. I think that's the one that you walked into the school knowing what HTTPS is, hopefully, or at least HTTP is a protocol. We see it in our URLs. So that's probably the most exposed to the end user. If you're explaining encryption, you say HTTPS means secure, it means it's encrypted. People go, oh, okay, I see it. They see it. It's right there. They can see it in their web browser. So secure emails. Email itself could be encrypted, the protocol. Again, something you want to check for under a security audit. Voice over IP, VoIP, very important. So VoIP gets overlooked a lot. VoIP server security, our voicemails. Voicemails might have inside of them some pretty business intelligence. If you're doing some kind of information about what's going on, you could even get a password over voicemail. Now listen to voicemails would be hectic, but it's possible if you get an executive's voicemails, those could be of some value. So, and last part, of course, IPsec. We want to add transparency to the security protocols, key management. So IPsec adds this deeper into the IP stack. The idea being original IPv4 was not very secure. Actually, there's no security at all really in it besides availability. That was actually built into with the routing protocols. That's built into the IP, but IPv6 brings in some more security. I don't know if I had some on that or not. So let's keep that in mind. The text will talk about it. And I think that covers what I want to talk about. Again, we'll look at here. Text summary. Again, the biggest walkaways is understanding the beginnings of how the keys are being generated. Are they using nonces, salting, things like that? Are they using modern modern, known, good protocols. Again, SSL labs, you can test for these type of stuff, security tests, or SSL security validation. And also, probably the most important one is, you can use tools like Nmap to look for this. Are we running any unsecure services on it, internally or externally or both? So an Nmap scan will determine this. So again, that covers the chapter. And the lab for this week, again, at the time of this recording, the NetLab itself is looking at the importance of data security and using encryption software. You can look at TrueCrypt container, and you're actually going to crack that, I believe, and look at the danger of having a weak key using TrueCrack. So don't forget lab itself. Information about the lab logins are here. Make sure you follow any pre-lab setups. Don't skip over those. And otherwise, I'm going to go through the lab itself. You can walk through it. And I think you just pretty straightforward. You'll see the danger of using a weak key. In this case, it'll be a TrueCrypt container. So that wraps up topic 4 on advanced cryptography. And I'll look forward to hopefully do some more videos here for you soon. Thanks.